All right, this is Tuesday, April 13th, 2021, Chemistry CP Period 8, and we're starting a new unit today, and it's called Nuclear Chemistry. Before I start showing the PowerPoint slides that go with this new unit, I feel like starting off with a review of stuff that I thought I had taught you earlier in the school year. And maybe I should even review the history a little bit. Thousands of years ago, the guy named Democritus philosophized and imagined if you took a piece of gold and you cut it in half, you still have some gold. And if you take that piece and you cut it in half, you still have some gold. And if you keep doing that over and over and over again, eventually you've got to get down to something that is so small, so tiny, that if you were to cut it in half, you would not actually have gold anymore. And we name that object an atom. We evolved over the centuries with the work of Dalton and then Rutherford and Bohr, and then more guys after that one. And our understanding of what an atom is has evolved over the years. And so at about the level of the Bohr model is all we need. We don't really need the modern quantum model of the atom for what we're about to do. But I'd like to remind you that in the Bohr model of the atom, we have two types of particles that are found in the nucleus of an atom. Those particles are protons and neutrons. And then surrounding them, as far as we're concerned, we can just draw a circle to represent it. Surrounding them are the electrons. Okay, the more modern view would be to say, oh, this is actually a probability cloud, and we're not sure at any one moment where the electron can be found. And that's all true, but it's not necessary to have that deep modern understanding for this new topic that we're going to be getting into. So, a little bit more reminder about atoms on the periodic table. So there's three types of particles that we've been dealing with so far. Oh, let's see. There's the proton, the neutron, and the electron. The symbol for the proton will often do a lowercase letter p, maybe with a plus sign as optionally. Neutron would be n, maybe with a zero. Electron, lowercase e with a minus sign. And so this is the symbol. This is the name. The electric charge would be the same as what you see here. So positive. I'll write the word neutral. This is why they're called neutrons, is because they have neutral charge. And then negative for the electron. And then there's the atomic mass units for these things, how much mass they have. Well, for the proton, it would be a 1. For the neutron, it would be a 1. And for the electron, they are so much smaller in mass than the other two that we just round it off and call it 0 as far as our record keeping goes. All right. Now, with these pieces, we have been building atoms to create the periodic table of the elements. And for any given element, which we represent usually by the capital letter X to represent any element. It's not xenon, it's just whatever element you want to talk about. The letter Z sometimes is written here, where Z is called the atomic number, and the atomic number is the number of protons. And this is the identity of an element. Whether it's gold or silver or carbon is strictly determined by how many protons we can count in its nucleus. In the upper left corner, I don't remember what symbol they use for it. I'm going to use the letter A today. A would be the atomic mass. On the periodic table, well, the one that I'm using, they don't write it as upper left superscript. They list the average atomic mass on the periodic table. So for copper, it says 63.546, for example. But on one given atom of any element, its atomic mass equals the number of protons. But that doesn't make sense, so there's more. So plus the number of neutrons. So as an example, if I had 18 protons and I had 22 neutrons, then the 18 tells me it must be argon. Only argon has 18 protons. So this is Ar. If you want to be redundant, you could write the 18 down below, but these both say exactly the same thing. It must be argon. And then for the atomic mass, you add these two together. 8 plus 2 is 10. 2 plus 2 is 4. And so this particular atom of argon has an atomic mass of 40. We also studied different isotopes. An isotope is different numbers of neutrons. So example would be carbon 12 versus carbon 14. Carbon 12, well, carbon by definition has 6 protons. Carbon is atomic number 6. So by definition, it has 6 protons. Any atom that has 6 protons by definition is called the carbon atom. What's different between these two isotopes is that carbon 12 has 6 neutrons because 6 plus 6 is 12, while carbon 14 has 8 neutrons. 8 plus 6 equals 14. I don't know what I said here. 6 plus 6 is 12. 8 plus 6 is 14. These are different isotopes. Now, in both of these atoms, we're treating them as neutral. And a neutral atom has the number of protons equals the number of electrons. If they are not equal, we call that an ion. Number of protons are not equal to the number of electrons. And then we even had a little bit of finesse to that and said, well, cation is when the number of protons are greater than the number of electrons, and the anions are where the number of protons are less than the number of electrons. So imagine that I wrote the word anion there. Okay, so that is a reminder of all the terminology that you students should have said, hey, Mr. Turek, let me write it for you. I have neater handwriting and I know all this stuff like the back of my hand, a colloquial expression that means you know it really well, and that you would have written all of this down without the slightest hesitation if I'd asked you to present this to your classmates for me. You would say, of course, I remember the history of our model of the atom. Of course, I remember the nucleus and the electrons orbiting it. Of course, I remember the names and symbols and charges and masses for the three subatomic particles. Of course, I remember atomic number determines the identity of the element. The mass number is the number of neutrons and protons. Of course, I remember what it means to be an isotope and how that's different from being an ion. Great. In fact, I'm going to now pause this recording because this is the fundamental stuff that it doesn't hurt to review at this time.